This video is about the solvent effects for SN1 reactions, and the take-home message from this is you definitely want a polar protic solvent, and in some sense you may actually need a polar protic solvent in order for this reaction to happen. And what is a polar protic solvent? Well, the canonical one would be something like water or maybe methanol. In other words, it's going to be something that has an OH or an NH bond, so alcohols are typical protic solvents. And that then creates a delta minus on the oxygen that the hydrogen is bound to, or the nitrogen, and it also creates a large delta plus on the hydrogen itself. And this is as opposed to polar aprotic solvents, where the example would be something like, say, DMSO, where you have a exposed delta minus but a buried delta plus. So this one over here has a big delta minus that's available because that oxygen is sticking out, but it has a delta plus that is relatively buried in the molecule and not as accessible. And that's really the primary difference between those two solvents. So methanol would be a classic polar protic, and DMSO does not contain the key OH bond, so that would be a aprotic solvent, which is to say no available proton. And the difference between these two solvents matters a lot for stabilizing the kinds of things that are going on over here. So the oxygen being minus means it can stabilize pluses really well. The plus being buried means it can't stabilize minuses all that well. And that was good when we were thinking about an SN2 reaction. However, when you are doing an actual SN1 reaction, the key thing that needs to happen is at some point the leaving group needs to leave just on its own. And what that does is create both a cation and an anion. And the most likely thing that happens before anything else is that the anion will rejoin with the cation and go back the way you came. So if this tends to fragment apart and your solvent's not good enough, like say DMSO, it is eminently possible that it will simply recombine. And this is an equilibrium step, but if the solvent doesn't allow you to separate the ions far enough from each other, then equilibrium will lie back in this direction. So not only do you need to form the cation and the anion, but then you need the solvent to get involved and to start pulling this away. And the H's of a polar protic solvent are well suited to do that because they are delta plus, and so they will end up surrounding this chloride on all sides, and that will be what helps to solvate the chloride and move it further away from the cation itself. Of course, the oxygens are going to be the part that are solvating the cation. So now I've drawn a handful of methanols surrounding that cation, but that's basically what's happening. The cation gets solvated by the oxygen part of the methanol, so the oxygens are attracted to that plus, and they tend to stabilize it, and that is, of course, why solvolysis reactions are so common with SN1 type substrates. But at the same time, what you need to do is use the proton, the delta plus end, to surround and solvate the nucleophile or the leaving group and surround that and separate it far enough from the two ions that then you can have something new react. And so the core idea is really well illustrated by the reaction coordinate diagrams over here, and that is, in an SN2 reaction, there is a delta plus in the middle of the key transition state, but there's a delta minus on either end, and what you're trying to do is lower the overall energy of that transition state relative to the energy of the starting materials. But a key feature of an SN2 reaction is that nucleophile, and if your solvent is too good, polar protic, what it will do is surround that nucleophile and lower the energy of that. And so while you're lowering the energy of the transition state some, you're lowering the energy of the nucleophile a lot. And so a polar protic solvent actually interferes with making that gap smaller. It may well make that gap bigger. But the analysis is different when you're thinking about an SN1 reaction. The key thing that you need to do here is lower the energy of this intermediate, and the intermediate is fully charged. And so the better your solvent, the lower you can make that intermediate. And the lower you make that well, the lower you're making the transition state hump that leads to that well. And so what you're ending up doing is making this distance shorter by having a better solvent. And unlike in the SN2, the nucleophile is really not important here. It doesn't get involved until there. And so this right here stays more or less steady, and what you're doing is lowering the energy of the charged intermediates relative to the uncharged neutral thing that you started with. So the moral of the story, again, is having the ability to stabilize both pluses and minuses is the key for an SN1 type reaction, where in the key step, you will definitely have both. You will have the leaving group having left, and it is a minus that needs to be pulled away from the carbocation that results. You have two full charges. The stronger your solvent, the easier it is to pull those two apart. Therefore, you really need a polar protic solvent to make that happen. In an SN2 case, you are actually not trying to pull anything apart. You're just trying to lower the energy of the system, and something that's not quite as good of a solvent is actually better, is actually desirable. For SN1, polar protic solvents. For SN2, polar aprotic solvent.